All right, welcome back everybody. Please grab your seats. If you're lucky, you may still get lunch. And with that, we'll start our seminar for today. We are almost through our very interesting and diverse list. November 20, one more seminar next week by a visitor who's already here. And today we have Jean-Philippe Avouac from Caltech. Now, we start here. Onamazu. Who speaks Japanese or reads kanji? Sounds like what? A nice dish, huh? Famous sushi dish. Onamazu. The earth shaker. Onamazu lives under the islands of Japan, guarded by the god Take Mikazuchi, who restrains the catfish with a stone. When Take Mikazuchi lets his god fail, Onamazu thrashes about, causing violent earthquakes. Earthquakes, punishment of the gods. That was obviously, in the medieval times, the only explanations we had. These images dramatically show consequences: Basel 1356, magnitude 6.5, or Lisbon earthquake, which we had covered before, of 1755. Earthquakes, a force of nature. But how? Only about 100 years ago, we begin to understand how earthquake works. At about the same time when relativity theory was developed. This is a famous fence of San Francisco, about 6 meters displacement, that led Harry Reid to develop elastic rebound theory. So he had an idea of the theory, but remember, at that time, the idea of plate tectonics didn't yet exist fully. This came only about in 1920s, 1930s. So there was no notion how these earthquakes really would have been driven. Earthquakes made by man, but how? That's an image on the left from the Koina Dam, which they started to construct in the 1940s. They started filling in 1962. And in 1967, a destructive earthquake occurred. Is that related to this dam? We can just go across the Red Sea. You see the Nile Valley. If you go down to the south, you see Aswan. On the left is the seismicity map. Almost no earthquakes, aside from this little cluster here, which is right underneath the Aswan Dam. Earthquakes made by man. But how? When you speak to press or anyone who's not, your family, your uncle, your grandmother, and you say you're working on earthquakes, the first question is, can you predict it? These are actual books you can buy on Amazon on earthquake prediction. Earthquakes cannot be predicted, says this famous paper from 1997. So where are we in this space of earthquakes, man-made or natural, and earthquake prediction? Well, we don't predict the weather, right? When you go online, you don't see the daily weather prediction. What you see is the daily earthquake weather forecast. So today we have Jean-Philippe Avouac from Caltech. He is the Earle Anthony Professor of, and now listen up, geology, mechanical, and civil engineering. So he covers all what we have in the room. And he told me yesterday that when he started his university studies, he signed up for fracture mechanics and astrophysics. Okay? which goes back to what we had in the other seminars, seeing pictures of outer space. Jean-Philippe is also the director of the National Science Foundation Center for Geomechanics and the Mitigation of Geohazards. He received his PhD in 1991 from Institut de Physique du Globe in Paris, and since 2002, he's at Caltech, and then had a stint working in the governmental institutions in France on safety of atomic facilities. And with that, I'll give the floor over to Jean-Philippe.
Okay, thank you very much, Martin, for the introduction and for the invitation to visit KAUST. I came here for the first time about 10 years ago, and I must say that I'm quite impressed to see how the campus has evolved, and also that KAUST is now on the map as a leading institution in academia worldwide. So it's a very great success. So today I'm going to give you a tour of the research we've been doing in my group related to earthquake forecasting. And I will talk about natural earthquakes, but also induced earthquake. I would argue that induced earthquakes are a curse. We certainly don't like to induce earthquake, especially when we produce geothermal energy or store CO2 in the ground. But at the same time, induced earthquakes have been a blessing for earthquake science because it has provided a way to understand better earthquake physics and develop actually earthquake forecasting methods. Let me start with a disclaimer about forecasting and prediction. So I certainly don't want to offend Benno Gutenberg, a former director of the Seismolab, who wrote this letter some years back. That was 1947. This laboratory does not predict earthquake. Specific predictions giving time and place come from amateurs, publicity seekers, believers in the occult, or just plain fools. So you will tell me at the end of the talk in which category I fall, but I've been avoiding using the vocabulary prediction after reading that letter. So what do we mean by earthquake forecasting? So here I'm referring to a definition that is an official definition. So in common language, we don't make much of a difference between earthquake prediction and earthquake forecasting. But in earthquake science, we have a definition. So an earthquake forecasting model is a systematic method for calculating the probabilities of target events within future space-time domains. So first thing, it's a probabilistic notion. So we're not trying to tell you when and where, how large will be the next earthquake. We are giving you a probability. So in the end, what we are doing is estimate the probability that an earthquake with magnitude exceeding a certain value m in a particular area A on a particular time window from time t to time t plus delta t. So that's really what we are after, is try to estimate this probability. So in the talk, I will talk about the probability of the earthquake rate, which is a simpler problem. Based on physics, I will show you that we can calculate the expected rate of probability. And then you can see the earthquake as a stochastic realization of that rate of earthquake predicted by the model. So I make a distinction between estimating the rate and estimating individual events. And in most of the talk, the events will be drawn randomly based on this estimation of the probability distribution function of the rate of earthquake. Okay, so the roadmap for the talk. I will start with basic notions of earthquake phenomenology and fault mechanics so that we are all on the same page. And then I will explain the principles that we use to forecast earthquakes. And then I will move to examples, starting with examples of earthquake induced by human activities. And then I will talk about the more difficult problem of forecasting natural earthquakes. I mentioned earthquakes and slow slip events. Slow slip events are a particular kind of earthquakes. I will explain that later in the talk, but they are a bit easier to forecast, so that's why we're using them to. Okay, so let's talk about the phenomenology of earthquake using the example of the Gorka earthquake, which is very well documented because the earthquake occurred beneath a network of high-rate GPS stations and seismic stations in Nepal, and so we were able to document quite in details the history of the rupture. So let's look at what we have on this map first. So we're looking at the front of the Himalaya. This is India here. This is Tibet. So the high Himalaya runs here. You have the Everest here. The red area here is represent the fault that is emerging at the front of the Himalaya. So India is thrust beneath that fault, beneath the Himalaya and Tibet. Okay. So this is the fault that is forming the Himalaya, basically. The red area represents the area of the fault that is locked in the interseismic period. In the long-term average, over many thousands of years, this fault is slipping at a rate of 2 centimeters per year. But we know from geodesy that currently it's locked. And we can demonstrate that it's locked from the surface to a distance of about 120 kilometers to the north. And that's the red area. Okay? So we know that this red area has to unlock once in a while so that all the slip is transferred to the front of the Himalaya, so that in the long run you have 2 centimeters of slip along that fault. This area now shows the area of the rupture of the Gorka earthquake. So 2015, it's a magnitude 7.8 earthquake, and the color scale is showing the amount of slip that occurred on that fault. So it goes up to about 8 meters. So this is that scale. So the earthquake started at the western end of the rupture and propagated eastward at a rate of about 2 to 3 kilometers per second. And we know that in great detail from the high-rate GPS station. So here I've put an example of the record of the ground motion in Kathmandu. So Kathmandu is here. And the 0 is the time at which the earthquake started at the far western end of the rupture. Okay? So you can see that at time 0, nothing happens in Kathmandu. Okay, it's far from the rupture, and that's expected. It takes time for the information to travel to Kathmandu. And, but you see that something like 40 seconds later, the ground started to move southward by about 2 meters in something like 10 seconds. Okay? And then it stops. And it stops relatively abruptly, but the earthquake itself, from the seismic records that we have globally, lasted for more than 1 minute. So the earthquake didn't stop. It slipped at this point that stopped. Okay? So what this record shows is that you have a zone of slip on the fault that is propagating from the epicenter here, eastward, and you're going to see an animation now that is illustrating that. So at the bottom right here, you have the slip rate on the fault as a function of time. The peak slip rate is about 1 centimeter per second on the fault. So this is the result of the inversion of the high rate data. So here is the animation. You can see the slip pulse propagating. Okay. So we understand pretty well now that earthquakes are generally of this kind. You have a slip pulse propagating, and then they stop. The map that you have at the top here shows the earthquakes that were recorded over the 20 years or something like that before the Gorka earthquake from a local seismic network that we deployed back in the 90s. And what you see is that all the earthquakes tend to line up along beneath the high Himalaya. That's more or less the front, the down deep end of the locked fault. This is where you have stress buildup. So you have all the time earthquakes happening at this zone of stress buildup because you have slip at depth and the fault is locked. So at the transition, you have a lot of stress building up. And the Gorka earthquake is not a lot different from this earthquake. It just grew a little bigger than these earthquakes. Clearly, this is not the kind of earthquakes that are actually transferring the slip to the front. You can see that the area that ruptured during that earthquake is a small area compared to the locked area. So that brings me to the kind of question we are trying to address with the research we do. Why is it that the Gorka earthquake didn't run all the way to the front? It was already 7.8. If it had run all the way to the front, it would have been larger than 8.5, probably. What's the probability that it happens in the next future, in the 10 years coming? What about this area here west of Kathmandu? This area, we know, hasn't produced any large earthquakes for something like 500 years. There is no earthquake for 500 years. 500 years, that's enough to accumulate a deficit of slip of about 10 meters. So if this area was to rupture today and release all the energy that has accumulated since the last documented historical event, it would be larger than 8.5, certainly. What's the probability that it happens in the next future? So these are the questions that we would like to be able to address. And I will show you the progress we've made. We don't have the answers yet, but we are making progress in developing a method to address these questions. So one word of earthquake phenomenology now. So here you see that you have one big fault, but you have a lot of smaller faults as well. And as a whole, the system is producing small and larger earthquakes. And when you look at the distribution of the magnitude of the earthquake, we have a well-known law that is called the Gutenberg-Richter law. I should have started with that. The Gutenberg-Richter law. And that says that, so what is plotted here is the number of earthquakes with magnitude above the value plotted in abscissa here. And you see that it decays. So when you go from magnitude 6 to 7, you have 10 times less earthquake. Okay, so you have much fewer large earthquakes than smaller earthquake. Okay, so that's a well-known property of an earthquake catalog. We see that at all scales. Even when you do a rock mechanic experiment in the lab, you produce acoustic emissions. These acoustic emissions are going to flow that law. The other phenomenological law that is important in earthquake sciences is the fact that earthquake can trigger other earthquakes. Okay? And earthquake can be triggered by remote loading as well. So you have two populations in general. Earthquakes that are independent from each other, that are triggered by the remote loading, and earthquakes that are dependent on other earthquakes, which we call aftershocks, but they could be foreshock to main shocks relationship as well. So a way to look at that is to plot the distance between two successive earthquakes in time and space. So here you have the distance in time. Here this is the distance in space. And here you find two modes in the distribution of those distances between earthquakes. You have one mode where the earthquakes are close in time and space. These are the earthquakes that are triggered by other earthquakes. The aftershocks and the foreshocks would fall in that mode. And then you have another mode that is more diffuse, which are the earthquakes that are more distant, that are independent from each other. And you can demonstrate that those earthquakes follow a Poisson process. Okay? So it's a memoryless process. And so generally, we can separate an earthquake catalog into main shocks that are considered independent from each other and dependent events, so aftershocks, which are going to be dependent on previous earthquakes. One other phenomenological law that might come up later in the talk is the Omori law. Once you have a large shock, you have aftershocks, and the number of earthquakes is going to increase as the logarithm of time, which is equivalent to say that the seismicity rate is decaying as 1/t after a large shock. This is the so-called Omori law. Okay, so these are well-known phenomenological laws. Okay, so this is, again, the distribution of earthquake magnitude for Nepal. Over the instrumental period, the largest earthquake we've had here is 7.8, the Gorkha earthquake that I mentioned earlier. How much bigger could be earthquakes there? To what distance, I mean, up to what magnitude can we expand that line? So we know that we cannot go to any magnitude because the earthquakes are releasing the strain that is accumulating when the fault is locked. So it has to be bounded. Okay, it has to be bounded. You cannot have an earthquake of any size. The elastic energy available to be released is finite. So this is also a difficult problem. That's the so-called MMAX problem, the maximum possible earthquake. And a way to deal with that problem is to do a simple budget. I will mention that later in some examples. So it's to say that the energy, the elastic energy that is stored as a fault is locked, that when the fault, is, I've shown you that map showing the locking pattern on the fault. So energy is building up, and then you said the earthquake are going to release that energy, and then you come up with a simple equation that gives you where you should end the theoretical Gutenberg law, so that you have a balance of the moment budget. You can see that as a balance of energy. And when you do that in the Himalaya, you find that you get a balance when the maximum earthquake is of the order of 8.8. Okay? So, okay, so now it looks like in this system we do need to have earthquake as large as 8.8. The question is when? This graph tells you the frequency, by the way, because this axis gives you the frequency of such an earthquake, so you know how frequently they should return. So such an earthquake should return every 1,000 years or so. We're talking of a very long period of time. Okay, so let's now talk about how we proceed to estimate the probability of an earthquake larger than a certain magnitude over a certain time window in a certain area. So we start from the Gutenberg-Richter distribution, and based on this distribution, you can look at the intersect with unity. If you have an earthquake above a certain magnitude, which is the magnitude of completeness of the catalog, you can calculate what is the expected maximum earthquake that you should observe for that time period. That's just simple statistics. We're assuming here that we're looking only at the main shocks. The aftershocks have been removed, so we're looking only at the independent events that are supposed to follow a Poisson process. So from this intersection, I mean, you get a simple equation. You can see that all you need to know is the number of earthquakes, how many earthquakes have occurred, and the slope of that curve, which is the B value that goes here, which is the slope of the Gutenberg-Richter distribution. Okay, so that shows that to estimate the hazard, actually what you really need to know is N, how many earthquakes you're going to observe in a certain time window. And based on this simple statistics, actually you can go to hazard curves. So let me show that. So the end product is represented here. And that's what is going to be useful for seismic hazard assessment or in practice for forecasting. What is plotted here is the probability of observing an earthquake with a magnitude larger than, let's say, 5.5, 3.5 to 5.5 as a function of time. Okay? So you see, for example, for that particular system, this is actually for Groningen in the Netherlands. I will show you how we got there later. If we look at, for example, at the probability of magnitude 4.5, this is the green curve. So the probability of observing 4.5 by 2015, according to that model, is something like 30%. Okay, and this is the kind of information that you're going to provide to civil engineers for seismic hazard assessment for building code, for example, to actually apply the building code. Okay, so now I've shown you that if we can estimate the number of earthquakes, so the number of earthquakes depends on the rate of earthquake, of course, on the time period you're looking at. If you can estimate n, then you have all the elements you need to do a forecast of the probability of having an earthquake above a certain magnitude in a certain area over a certain time window. So we need to estimate the A value of the Gutenberg-Richter law. So how high is this curve? We need to determine the B value and eventually where to end the distribution. Where to end the distribution doesn't matter too much. Most of the time you can assume that it's not ended because the probability of very large earthquakes is generally very small. But that's an issue that can come up in certain cases. So there are 4 quantities that you need to estimate, which may vary in time and space. Well, this one I didn't talk about. If we assume a tapered Gutenberg-Richter distribution, there is this additional parameter, but I won't talk about that today. Okay, so the question is how to estimate those quantities now. Let's look at the simplest model you can think of an earthquake. So it has been realized early in the 70s that earthquakes result from stick-slip behavior, from slip instability due to friction. And the simplest analog model of an earthquake is a spring slider system. You imagine that you pull on the slider with a spring until the friction cannot resist anymore the force due to the spring, and then the slider might move in slip events. So here is a demonstration of my earthquake machine by my 2 favorite assistants. That was 20 years ago. And so you see the principle. So this is the simplest model of the earthquake cycle. So in this model, you of course, if you have only one fault and you're pulling at a constant rate, all that happens is going to have a periodic return of the same slip event if friction doesn't change. So it takes a bit of time to load the system until you reach the static friction, and then the friction drops to the dynamic friction, and that repeats. So you get a periodic return of a slip event. So this is more or less the principle of the standard Coulomb failure model that we use in earthquake science. Okay, so an implication of that very simple model is that the rate of earthquakes here depends on how fast you're pulling the system, right? How fast you're turning the crank. So the seismicity rate is proportional to the stressing rate or the strain rate equivalently in this system. Okay, so in reality, faults can be loaded because you increase the shear stress or because you change the normal stress. So the standard quantity that is used to evaluate the probability of failure is to calculate the change in Coulomb stress. So in that diagram where you have the normal stress and the shear stress, the blue line represents the condition for a slip instability, for activation of a fault. And let's say that you have a fault that sits initially here at this normal stress and on this shear stress, and that you change the stress either by augmenting the shear stress, turning the crank, or by changing the normal stress, or by changing the pore pressure, because what matters here is, what is plotted here is the effective normal stress, the difference between the normal stress and the pore pressure if you have fluids in your fault. So there are different ways that you can bring a fault to instability, and this equation captures all those possibilities: the change in the shear stress, the change in the normal stress, or the change in the pore pressure. So we calculate what we call the Coulomb stress change. So it's the change in shear stress minus the friction time the change in effective normal stress, and that tells you how much closer you get to failure. So we know that this quantity does quite well, for example, at forecasting the spatial distribution of aftershocks following a large earthquake. This was established in the 90s by people like Jeff King, Rothstein, and this is an example of the distribution of aftershocks following the Londres earthquake. The white dots are the aftershocks, and the color scale is showing in red area of increased Coulomb stress, so where the medium was brought closer to failure, and in blue where it was moved away from failure. And you see that most of the aftershocks are falling in areas of increased Coulomb stress. So this very simple rationale works quite well to explain distribution of aftershocks. Okay, so as I said already, in this very simple rationale, the seismicity rate R at time t divided by the background rate, the rate of earthquakes due to tectonic loading, is proportional to the stressing rate, the ratio of the stressing rate to the background stressing rate. So that provides a relatively simple way to forecast the seismicity rate. Let's look at what we expect. For example, if we have an increase of Coulomb stress over a certain time window, and then it gets stable. With this model, as soon as the Coulomb stress starts to increase, if you have a population of faults that are initially close to instability, you would get a uniform seismicity rate. You would have immediately earthquakes, and it would be uniform. And as soon as you stop loading the faults, it should stop. So it's a very simple relationship. We know that actually this doesn't work, really. One reason is that if that model was right, the earthquake would be synchronized with tides, with solid earth tides, because that's where you get the peak stress. And people have looked at that for a long time, and there's sometimes a very weak correlation, but most of the time there is no correlation. And the understanding is that there's something wrong here, which is the assumption that as soon as you reach the condition for failure, an earthquake occurs instantaneously. In fact, it takes time for an earthquake to grow, to nucleate and to grow. And so now we have models of earthquake nucleation that are based on friction experiments. So we know that friction is a little more elaborate than this simple model of static to dynamic. And so we're using friction laws derived from the lab that are called rate-on-state frictions, rate-on-state friction laws. And here you have an example of such a friction law. So mu is the friction coefficient, so the ratio of the shear stress to the normal stress. It depends on the log of the sliding velocity, so V is the sliding velocity, and on some state variable, theta, which can have different meaning, but the key element of that, the key effect of that state variable is that it's going to allow healing. So each time you have a slip event, the fault re-strengthens, and that's because we have this state variable in the law that it can happen. And that's why you get stick slip event. Okay? So that's sort of the simplest law that's going to produce repeating stick slip event because it heals after each slip event. And so this law fits relatively well laboratory data. And the second equation expresses how the state variable evolve as a function of time and as a function of the sliding velocity. So you need to solve that system of equation to actually simulate the nucleation of an earthquake. Okay, so the key element here is that with these equations, a fault always creeps, in fact. There is no notion of a fully locked fault or sliding fault, but it creeps at very slow rate most of the time. So this is the log here of the the slip rate as a function of time. So most of the time, it slips at extremely slow rate, and then you have an acceleration toward rupture. Okay, this is a prediction from those models. So the rupture process is not instantaneous. That's a key element. So we will see that that's something that helps fitting observations. So without explaining how we derived that, I mean, you can come up with an equation that is now a bit more complicated from what I've shown earlier, but the spirit is the same. It shows the seismicity rate as a function of time, R, divided by the background seismicity rate, and it shows how it varies with the Coulomb stress change. So delta ST is the change of Coulomb stress since the initiation of the perturbations. It could be tectonic loading, or it could be operation of a reservoir for induced earthquake. Okay? So here you have now an equation to make a forward prediction of the seismicity rate as a function of time. All you need to know is the parameters of that law. So you need to know this A value, B value, on the sub C. So it's a few parameters that are coming into into play. Let's now look at what is the response of a system now to a ramp increase of the Coulomb stress. So now, with this equation, rather than having a plateau in the seismicity rate, you're going to have two things. First, there's a delay if the population of fault is not critical to get started. Let's say that the area has been quiet for a long period of time, and the fault have time to relax, they heal, and so you're not going to have seismicity right away. So there's a response here that is delayed in time. And then the seismicity rate increases smoothly depending on how fast the earthquakes are nucleating. So depending on the nucleation process, you can have a very rapid increase or a smoother increase of the seismicity. And when you stop the perturbation, the seismicity rate is going to decay with time. And the decay depends again on the nucleation process. Okay, so let's now see how this model performs, starting with an example from induced seismicity. The first example will be an example that we have studied a lot in my group. This is earthquakes induced by gas extraction in the Netherlands from the Groningen gas field. So the Groningen gas field is the largest continental gas field in Western Europe. And it's been in production since the 60s. Here in blue, it's the gas production rate. You see that it's seasonal because they need more gas in the winter than in the summer. And so this is the cumulated volume of gas that has been extracted from the subsurface. The gas comes from a reservoir that is at the depth of about 3 kilometers, and the reservoir is relatively thin, about 200, 300 meters. So at the beginning, not much happened. The only issue was subsidence. So at the top, you have the subsidence, which occurred from the start due to the depletion, to the drop of pressure in the reservoir. But starting in the 80s, in the 90s, they started to observe earthquakes. And the number of earthquakes started to increase exponentially. Right? And that's on something like in 2015 or so, I got in contact with Shell, who were interested in developing a model so that we could predict where this was going, because it was still exponential at the time. So yeah, the people were a little worried about where this was going. So let's see how far we've gone in explaining those observations. So we have to explain the delay of something like 30 years, 40 years in the onset of seismicity, and we have to explain the time evolution of the seismicity, right? So the initial exponential increase. So to do that, it has taken a bit of time because we have to build a complete workflow that goes from the reservoir modeling. So we have 3 modules in our workflow. The first one is informed with the information about the location of the wells, the flow rate, the pressure at the wells. So this is the reservoir modeling part, the standard reservoir modeling that is done in the oil and gas industry. Then we use the prediction from that model in terms of the pore pressure distribution in the subsurface to inform a geomechanical model that's going to predict deformation of the medium, including surface deformation that we can measure with GPS and INSAR. This is important because when we have such information, we can validate and calibrate the geomechanical model. Okay? And then this geomechanical model can be used to calculate stress changes in the subsurface, which you can use to drive the seismicity with the equations, with the equation I just introduced. And so that leads me to the last module, which is the seismicity model, which you calibrate and validate using the observed seismicity. Okay? And once you have the whole workflow, you can actually you can do earthquake forecasting. Okay? So let's see how this works. So this is the reservoir modeling part. I show that because what I'm going to show requires a lot of calculation because all the models are, the parameters of the model are determined using an inversion. So we use MCMC, so a Monte Carlo Markov chain technique. So it requires a lot of calculation. So we need to have very efficient models. So for example, for the reservoir model, we don't use a full 3D multi-phase model. We use a vertical flow equilibrium model. We solve only for the pore pressure distribution in 2D. And then we assume that we have hydrostatic equilibrium vertically. And with, for example, such a model, we fit very well all the pressure data from the wells. The fit is gives you a RMSE, a root mean square of 0.6 megapascal. The operator, NAM, has a much more sophisticated model, but the fit to the data is 0.5 megapascal. So it's, you know, it's not that different in the end, okay? So reservoir model, our reservoir model works pretty well. Then the geomechanical model, same thing. We are not going to do a very complex geomechanical model. We use semi-analytical green functions. So we represent the reservoir by cuboids. Okay, so, and here this diagram shows that the cuboids are offset because as you will see later, the reservoir is faulted. So we take into account those discontinuities in the reservoir. They are important to explain the seismicity. And so we discretize the reservoir in cuboids, and then we calculate the deformation in the medium using elastic green function. The quantity that we need to determine when we do that is the compressibility. So it's the uniaxial compressibility, how much vertical compaction you get from a certain drop of the pore pressure. Okay, that's the quantity that's going to drive the deformation, the stress changes in the surface. Okay, and once you have that, then you can calculate the displacement and the stress changes everywhere in the medium, and that's going to feed the seismicity model. Okay, so let's look at the data, starting with the surface deformation. So we are using displacement measure from leveling. So this is vertical displacement that covers the whole period since the beginning of gas production at Groningen. Here we have GPS stations. We have, in that case, the vertical and the horizontal displacement. And then on the left, you have the INSAR time series. So that gives you the line of sight, so the displacement toward the satellite. But that's very dense in space. So you have a lot of information from the INSAR. I don't go into the detail of that, but I just show one thing. When you combine all those data, you can actually identify the different sources of deformation in your data, and we use an independent component analysis for that. So I'm showing the two dominant components that we get when we do that. So one is the one we are looking for. This component shows the outline of the subsidence, and you see that it's clearly the subsidence related to the Groningen gas field because it corresponds with the footprint of the gas reservoir. So here you have the spatial distribution of that component, and here this is the time evolution of the subsidence, and it follows more or less the gas production. Okay, so no surprise here. We need that information to calibrate the geomechanical model. Something that was not anticipated, we had another component that was not obvious in the data, but that became very obvious after we did that analysis. And then we contacted the operator and said, well, do you know, is there anything happening in that area? And so that's a reservoir that they actually use for a seasonal storage. So they store the gas produced from Groningen to have a larger reserve available in the winter. And this one is very seasonal and it's very small, but it's a cute signal that we can use to validate our workflow. Okay, so let's start with this one. So here you have the surface displacement over that small reservoir, the gas storage site of Norge. You have different colors here, different ascending and descending track with Sentinel. And there's a GPS station at the same location, which is shown in pink. So you can see that the INSA and the GPS tell you the exact same surface displacement. All looks good. The blue line is the pressure in the reservoir that we calculated with our reservoir model. You see that there's a shift between the pressure at the point where it's calculated and on the displacement at the point where it's calculated, where it's measured. That's the time for pore pressure diffusion, in fact. And you can see that because the continuous red line is the prediction of the geomechanical model. You can see that the geomechanical model is exactly on spot with the observation. When you do that, you invert for one parameter, which is the compressibility of that particular reservoir. So that reservoir is so small that we cannot map spatial variation of compressibility. We get one value. For the Groningen gas field, we can do the same thing. And in that case, we do need to account for spatial variation of the compressibility. It's not uniform. There are places where the facies of the reservoir, it's a sandstone reservoir, varies, and so the compressibility will be different. So now we have the compressibility. We can calculate stress changes at the location of the earthquake. So we need to look also at the earthquake. Where do they happen? So here, this is a map of the distribution of hypocenter as a function of depth produced by back projecting the wave field recorded by the stations above the reservoir. And you can see that you have a clear peak in the hypocentral distribution at the top of the reservoir. So it could be in the cap rock or in the reservoir. We don't all agree on that. I tend to think they initiate in the cap rock, but it's a very peak distribution. Okay, so let's move now to the Coulomb stress changes. So we know where the earthquake is happening at the top of the reservoir. On this map are showing the stress changes calculated where the earthquake is happening as at different for different time period. So this is in 2009, and so you see that the Coulomb stress is increasing. So why is it that we have a Coulomb stress increase? That's because the reservoir is offset by the faults, so you have stress concentration where the faults are offsetting the reservoir. If the reservoir was uniform, the ground would be just subsiding smoothly and there would be no stress concentration. There should not be any earthquake triggered by gas extraction in that context. So here we do have Coulomb stress increase because of those faults offsetting the reservoir. Okay, so now we have the Coulomb stress distribution. And we can determine the parameters of the seismicity model to fit the seismicity observation. So for that, we cut the seismicity catalog in two. We use the first half to train the model, to determine the model parameters, and we use the second half to validate. So we invert for the model parameters. I don't not going to go into the detail of that, but the inversion is relatively well posed and the model parameters are relatively well determined. And so you have the values here. An important parameter here is delta SC, is the threshold, is how far you were from failure when they started producing gas from Groningen. That determines the delay, the fact that it took 40 years to compensate for this initial distance from failure before they got the first earthquake. Okay, the other parameters are going to determine more the time evolution of the seismicity. So this is the pattern of seismicity that is observed. This is the prediction from the model. And you see that the fit is relatively well. And now here you have the comparison between the observed seismicity. So the blue line is how many earthquakes are observed every year. The cyan line is the best fitting model, the prediction from the best fitting model. And then the other line are showing the uncertainties. So you have a distinction between epistemic uncertainties, the uncertainties that are related to the determination of the model parameters, and you have the aleatoric uncertainty, which is taking into account that the earthquakes are drawn from randomly as a stochastic process from the estimated seismicity rate. Anyway, so you can see that the model fit the observation pretty well during the validation, the training period, and when you look at the validation period, it's on spot. Okay, so the model does quite well. One thing about the nucleation process. So here we are using this nucleation process that is time dependent. Do we need it? How well can we do if we assume that the earthquakes are instantaneous? So there's something interesting at Groningen is that the seasonal the production of gas is seasonal. So you do have seasonal variation of stress. And so it's interesting to see if we do detect a response of the seismicity to the seasonal stress changes. It's not easy to see because it's a point process and you don't have thousands of earthquakes, so it's not a trivial problem. So the way we look at that is to use a test that was introduced by Schuster in the 19th century to look at really the correlation between earthquake and solid earth tide already. And the way it works is it's an elegant way of doing it. The way it works is relatively simple. You go around the clock over 1 year. And so he was doing that for tide. So he was using the period of the tide. So he was using 12 hours or the moon month. But here we are doing that over a year. So we go around the clock in 1 year, and each time there's an earthquake, you make a step in the direction that corresponds to the time of that earthquake. If the earthquakes are distributed uniformly around the year, you should go back after 1 year to the origin point. Okay, and if you repeat over many years, there should be no drift. You should stay around the origin of that diagram. So what you see clearly here is that from year to year, you have a clear drift. That indicates that you have an excess seismicity in March, and it is significant. Actually, you can, you see, for example, that to reach that far away from the origin, the probability of going that far away from the origin is 0.1% if you assume that the earthquake follow a Poisson process. So it is a very significant signal. So then you can look at what you would expect if earthquake were instantaneous. So we do the forward modeling. We assume that the earthquakes are instantaneous, and then we see that we should have a much stronger response to seasonal variation of stress, and also the phase would not be right. The earthquake rate should peak in January, not in March, and we should be seeing a stronger variation. So I think it's a nice example that demonstrates that the nucleation process is time dependent, and more importantly, you can actually constrain the duration of the nucleation process. So in practice, it's of the order of 0.1 to 1 year. So the nucleation process in that model depends on the stressing rate. That's why you have a range. The stressing rate is not uniform. Okay. So let's move to now how the model fits earthquake magnitude distribution. So here in red, this is the distribution of earthquake magnitude observed at Groningen. The blue is the prediction of the model, and the gray lines are showing the uncertainty predicted by the model. So you can see that the model fits relatively well the magnitude, and that's because they follow the Tabel-Richter distribution, basically, and we have the right number predicted by the model. So then you can read, so that first plot was up to 2009, and you see that as you advance in time, you always fit the data relatively well. You can compare the expected maximum magnitude in blue with the observed maximum magnitude in red. So all falls in place. Here you have a tool that is relatively now solid to do the earthquake forecasting and produce this kind of curve that are showing the probability of exceeding a certain magnitude going further in the future, because the model can be run in the future if you have a scenario of production. Okay, so I've shown you in some details how the forecasting method works for gas extraction, and I hope I convince you it does a good job. Here, this is going to be a vignette to show how it works in the very different context of wastewater injection. So we're looking at Oklahoma. So in the Midwest, you know that this is a place that is producing a lot of earthquakes, more earthquakes than in California. This is related mostly to injection of wastewater from fracking. And so on the right, you have in green the volume of water that has been injected in Oklahoma as a function of time. In red, you have the seismicity observed in Oklahoma, and you see that you have a clear shift, like in Groningen, but the shift is not of 40 years now. The shift is more of the order of years, okay? And here, what is interesting, the earthquake occur not in the cap rock, but actually in the basement. So, same thing, we calculate the Coulomb stress changes, and we adjust the model parameters. So here, this is the prediction of the seismicity in space. So the black dots are the earthquake that were observed. The color shading is showing the predicted distribution of seismicity rate. And to the right here, you have the observed seismicity, annual seismicity in red, and the blue is the prediction from the best fitting model. So it's on spot. So it's the exact same workflow, but now run in a context of injection. So this is a simple scenario because the injection rates are relatively uniform, and we looked at a context that is actually more challenging, which is a context of development of an enhanced geothermal system, so EGS. So in that case, it's very different. It's also injection, but they are actually inducing earthquake on purpose because they want to fracture the rock to create, to augment the permeability in the subsurface. So we're going to see that the same model works quite well. So here you have a view of that particular experiment, which was run near Helsinki at a depth of 6 kilometers. You have the well at depth with the different segment of the wellbore that were actually fracked. So they started hydrofracturing from the bottom, as they always do, and then they moved up. And then you have the seismicity in the background. Here you have the distribution of seismicity as a function of distance from the well with time. And you can see that it doesn't follow the standard equation from diffusion because actually they used a quite sophisticated, complicated schedule here, which is shown here. So here, this is the seismicity rate during the experiment, and this is time. And in orange, this is the injection rate, so the flow rate at the wellhead. And you see that they had periods of injection at high rate, a shut-in, they would start injecting again, shut-in, they would vary the shut-in period, and they would vary also the flow rate. So it's a very complicated pattern. It's not a simple model. When the shut-in, by the way, you do have actually a pore pressure, a decay of seismicity that is very much the same as what we see for aftershock. So it is a numeric low decay as well. Now I'm showing straight the result of the model prediction. We use the first stage to adjust the model parameters. So only that period was used. And you can see the observed seismicity, the black line, and the purple line is the prediction from the model with the uncertainty range. And for all the other stages, it's a prediction of the model. And you can see that the evolution with time is pretty good. It does predict the right decay of seismicity each time there's a shut-in. And the decay here is fit not because of the nucleation process, but because of pore pressure diffusion. And here, this is the fit to the distribution of earthquake with distance from the well. And the model does relatively well at explaining so the evolution in time and space of the seismicity. Okay, so now let's discuss how we can transfer this learning to natural earthquakes. So let's look at the Himalaya. So the difficulty with natural earthquake is that they are driven by deformation, right? So it's not like pore pressure diffusion due to an injection or so on. So we're going to use geodesy actually to calculate the stress changes. So and it is rather uniform in time, but variable in space. And so here you have the seismicity observed in the area of the India region of the India-Eurasia collision. And here, this is the strain map derived from seismicity. If the medium is elastic, then the elastic stresses are going to be proportional to the strain rate. So we can test that prediction. And you see that the seismicity rate, you bin the earthquake based on the strain rate, and you find that the seismicity rate is linearly proportional to the strain rate, which is the expectation from the model I've shown earlier. So we can explain pretty well the distribution of seismicity in space now, based on the geodetic data, using the same model we've been using for induced earthquakes. So I'm running out of time, but let me just say in a word the key points that we can make at this point. So with geodesy, you can calculate stress changes. You can turn that into seismicity rate, and that you can use that directly to feed a probabilistic seismic hazard workflow, and you can produce this kind of map. And this is what we produced based just on the geodetic data, on the seismicity data. So that shows the PGA, the peak ground acceleration, that has a 10% of probability to be exceeded in 50 years. And this is what the engineers want for the building code, right? On the right, this is the result of a study that is using the standard technique. Okay, so this is just to show that the same physics can be used to forecast distribution, to forecast the distribution of earthquake in space. What about time of individual events? And I will stop with this prospect. So the real difficulty is that this kind of technique is time independent. It tells you the probability of having an earthquake or a certain ground acceleration in the coming 50 years, but it doesn't tell you that it's the 50 years coming next. It doesn't take into account when was the last earthquake. So it doesn't take into account how much energy is available in the system at that moment to drive the earthquake. And so we're working on this at the moment at Caltech. And the good news is that based on return state friction and dynamic modeling, we can actually make progress on determining the probability of larger events, but we are not quite there in terms of predicting the next earthquake on the San Andreas Fault. So I should stop there, and I'd be happy to take your questions. Thank you for your attention.
Thank you. So the earthquake prediction problem is not solved. And if someone says the constellation of Saturn and Neptune tell us that earthquakes will happen next week, we probably shouldn't believe.
Probably not.
Okay, questions, and as usual, from students first. I see Jörg's hand coming up.
Thank you for your nice talk. And your example from the Netherlands, above your reservoir, you have this Zechstein, which is a lot of evaporites. Do you think it matters if you have a huge sequence of evaporites on top, or if it's a brittle lithology?
Yes, so that was a debate at the beginning regarding whether the surface deformation was due only, for example, to the reservoir compaction, or whether there was any flow in the salt layer on top. My take is that it looks like the response of the salt is negligible because we can fit the observation extremely well with an elastic model, and in effect, the stress changes in the salt layer are very small. So I don't think that it plays much of a role in that story. You could have anything above it, and I think you would get a very similar story. Yeah.
Okay.
Maybe the earthquake could grow bigger because the salt is not known to be very seismogenic. That's the difference.
Thank you. So, is the subsidence is it a product of the compaction of the reservoir, or is it induced by tectonic faulting? Because if it's reservoir dependent, can we classify which ones are more likely to develop seismicity and which ones are not?
Okay, so again, in the context of the Groningen gas field, right? So you have to imagine that those faults were pre-existing, right? That the system has been quiet for a long period of time. So those faults were not going to produce any earthquake in absence of a perturbation. Okay, so you are in a context where, in absence of a perturbation, you would probably not get much earthquakes. So it's really the gas compaction and the stress concentration at the places where the reservoir is faulted that produce the earthquake. The earthquake don't need to happen on the faults, by the way. They can happen away from the faults are serving as a place of stress concentrations. Okay? So the earthquakes are clearly related to the operation, but of course it depends on what was the initial stress, which depend on the past tectonic history.
Thank you.
Other questions? Students, postdocs, faculty, blown away, hungry? Oh, Matteo, okay. Great. And showing you user?
Yes, yeah, it works, yeah.
Okay. Just take it very close.
Okay, very nice talk. I'm a geophysicist, I'm not deep into this topic, so it's very curious to see how you sort of approach the problem. It's very nice. But I guess this question had to come from someone, so I will be the one taking this responsibility. There's been a lot of, I don't know, you could call it excitement or disillusion or whatever, of machine learning being able to solve this type of problem. What is your opinion on this? And the disclaimer, I do machine learning, but not for this problem, so I have no stake in this. It's just a curiosity question.
Okay, so machine learning can be useful, but the first thing is to demonstrate that your system is chaotic but deterministic, right? So that you have a predictable horizon, because let's say that you have a periodic pattern, any algorithm would actually fit the periodic pattern and would actually fit the observation, as long as you don't move away from the periodic pattern. So if you have a chaotic system, it looks periodic for a little while, and then you have a jump to a different mode. Machine learning is not going to capture that very easily. And also, if you don't know that this jump can happen, it's not going to work. So I'm a little skeptical about using machine learning for for this kind of thing. That being said, for example, for Cascadia, there has been quite a lot of work done on slow earthquake on Cascadia. I was planned to talk about it, but I didn't because I was a little too slow. You look at the slow earthquake in Cascadia, we have a large catalog, and that's the advantage of the slow earthquake, because they return every year instead of every 1,000 years, right? And so when you look at the pattern, it is actually chaotic. You can demonstrate, and you can demonstrate that the predictable horizon is of the order of something like 3 weeks. Okay, so it is chaotic, but not to the point that you cannot make a forecast. So I think that in that case, you can forecast slow earthquakes, and actually machine learning then does the job. Once you have demonstrated that you can do it, that you know the predictable horizon, you can use any tool you want to do it. That would work. But if you go beyond 15 days, it's really not beyond three weeks, then it would probably not work. Yeah.
Thank you.
Yeah.
Going back to the very beginning, Martin showed a slide with the title, Earthquakes Cannot Be Predicted. Now, we also know, like you showed, that earthquakes don't happen at peak stress. And I guess some would argue that's when you have the title, peak stress, you don't get instantaneous triggering. So one might argue then, therefore, there is some kind of a preparatory process before the earthquake takes place. What are your thoughts on that, of trying to detect that potential preparatory process?
Okay, so we've run simulations with our earthquake simulator, so it's a bit similar to the one that Olaf has developed with Martin. In a system like that, you have a self-organization of the stress. I mean, initially you produce few earthquakes randomly, and then after a little while you see that you are on a particular orbit, so it is chaotic, but you have a strange attractor, you are in a certain orbit, and that makes it actually possible to do a forecast over a limited horizon, because you have this self-organization of the stress distribution. A fault rupture, it redistributes stress on the other faults, and then you are locked in a certain range of the phase space, so that you have a strange attractor, and we see that in numerical simulations. So that gives a little bit of hope. The problem is to use observations to actually determine where you are in this strange attractor, and so you would need to do geodesy over many thousands of years to actually build the strange attractor. So we are trying to explore the possibility to use geodesy and complement with past historical data to see if we can do that. And I'm not too hopeful, but we'll see.
All right, we hit 1 o'clock. Time to go. Thank you again, Jean-Philippe.